Hello and welcome to today's talk on NEWROMAP, a mapping tool for convolutional neural networks to edge AI accelerators. So let's first take a look at the main challenges for edge AI accelerators today on the market. So the application requirements are usually that we want to have real-time processing and on-device computing. And this means that we need devices that have low power and low latency. On the other hand, for most visual tasks like this bounding box detection here of the stop sign, we conventionally use convolutional neural networks, which, as you probably all know, have the issue of a high compute load, but also high compressibility, which we can use in our advantage. But in general, the high compute load and the requirements for low power and low latency are contradictory. And so one solution for these are scaled out self-contained neuromorphic accelerators. So what are these kind of accelerators? Let's first take a look at the products available at the market today. So this was in collaboration with Grey Matter Labs. They proposed an edge AI accelerator, but we find similar design concepts also from Intel or from Xilinx. In general, scaled out means what you can see here on this side as well. It is a massive multi-core system with something like 128 plus cores. And self-contained means that you map the whole neural network to the accelerator and you do not reload the neural network during inference. So you have large but limited core memory, and you do some sort of near or in-memory compute scheme without external cache access. And then what you find in all of these products is that they are NOC interconnected, usually using something like a 2D mesh and XY routing, so relatively conventional architecture. And the research question here is, how do we bring CNN workloads to these kind of systems? So let's revisit the CNN again, and what you can see here, as you probably all know, it has some inputs and then a data flow through multiple hidden layers, and then finally you get the output classified result. And now we want to bring it to this kind of accelerator. So as I said, it's NOC interconnected. You can see this here with the routers in green. And it is self-contained, meaning that you want to bring the whole neural network onto the design. So this is what we showed here in this small pictogram, that, for instance, the first layer is mapped to the first core, and the second layer is then split up in half and mapped to the third and second core. And then these accelerators use data flow processing. So basically, you see that the data flow through this mapped design as they would also flow through the convolutional neural network. Okay, so that motivates our talk. So you saw there's a high demand for low latency and low power processing, and these neuromorphic accelerators are one possible solution for that. And then our research question is, how do we bring these CNN workloads to these kind of architectures? And our solution is a snake mapping, which uses a two-step approach. And then we also do a further optimization of the snake mapping with a tool that we call NEWROMAP. And then the results that we get are an evaluation of the NOC performance with industrial benchmarks, ResNet and MobileNet v2. And then finally, we can conclude our talk, and we will find that we, of course, improve latency and power as you expected, but actually with some quite nice results of up to 4x better bandwidth and 22% better latency. So stay with me and see how we achieve that. Okay, so let's first go into our solution. So what I already said are the requirements of the two conventional architectures in this domain, but I would like to reiterate them. So we do this near memory computing, so we need to distribute the load over all cores equally. And we also have memory that in the architecture is equally distributed. And since it's self-contained, we are bound by the amount of memory that we actually have available. And then the cores usually only exchange the activated neuron weights. So we have a weight stationary data flow that only commits part of the data, which goes then towards this idea of sparsity. So if you just revisit again our CNN, so what you can see here is something like a prevalent data flow, right? And this is this feed-forward characteristic that is present in nearly all CNNs. And so if we want to find a mapping function that maps the neural network to the network graph, so NN for neural network and NG for the network graph, what you can now see is there's a very clear solution idea for this, namely that we can do something like a snake mapping, which just folds this forward path characteristics in an S shape over all these cores. So basically you can just lay them linearly over the mesh. And by that you can directly minimize data flow and latency here measured in terms of the sum communication weights over all links and the average deviation from the compute load. So that's quite cool, right? So how do we do this mathematically? So we have a CNN graph, which we call NN here, and we're looking for this mapping function, and we want to minimize the communication subject to the load, core, and the memory bounds, and then we map this to our NOC graph. And we do this in a two-step approach. So first we do the core allocation, and we map into an intermediate representation, and this distributes the load equally over the cores. And then for the intermediate representation, we have one additional constraint, namely that it has the same size as the network graph. And then we can do something that you all know, conventional NOC mapping, known for years. So we can just map from the intermediate representation to the network graph, and we are done. So that's something you already know. And we pack this into this whole NEWROMAP tool. And what does it do for us? So we have a target application and a target platform inside our tool. So you can set the frame rate, the video resolution, you can give it a TensorFlow model, and then also NOC parameters like the topology. And then inside the tool, we have an interface unit that integrates to TensorFlow. Then we do the IR generation and the initial mapping as shown on the previous slide, which is basically just our snake mapping. Then in the next step, we additionally do a simulated annealing to further optimize for the communication. So we mainly do this for showcasing how much more potential there is to improve the mapping. This is of course clear that simulated annealing is a relatively naive approach, but this is just here taken as an example to show further optimization potential. And then finally, we simulate the NOC. Okay, let's take a look from our approach to our results. So how good is it actually what we're doing here? So what is our case study? This was developed in collaboration with our industrial partner, and it reflects these typical properties of these edge accelerators. So we have a scaled out chip, but we tested 4x4 to 12x12 AI cores to see how good does it work with scaling. We do 32 MAC operations per tile with a 1 GHz clock frequency. We use conventional XY routing and 32-bit large weights in our neural network with conventional input resolutions that you would find in academic papers and 30 frames per second. So basically something that looks similar like this here. So first we compare our snake mapping versus a random mapping, because there has not been any mapping approaches in these edge AI accelerators before. So we wanted to have a fair comparison against some decent baseline to understand how good do we actually get with this naive approach. And so what you can see here is always the mean of our random mappings. We did 1,000 random mappings and the standard deviation, and then how good is our snake mapping. And then what you can see here in green for ResNet and in orange for MobileNet, that we of course are better, but how much are we better? And for ResNet it's actually quite nice. We get some 3.8x improvement in terms of the total bandwidth inside our NOC. Then we also took a look at the average hop distance of our mapping, which is somewhat proportional to the latency that we expect. And here again, you can see a larger improvement for ResNet with up to 3.7x. But in general, both approaches, in both networks, we are better with our approach than for random mapping. So we see a large improvement versus a random mapping, but that's expected because we are more clever than random mapping, right? So the natural second question is, how good are we actually with this initial mapping, and how much further could we get? And as I said, we are using simulated annealing for this as a showcase. And then what you can see here is again the total bandwidth after optimizing our snake mapping with simulated annealing. And then you can see from ResNet we are actually at the global optima here at the beginning, but then at the end we can get something like 30 to 40% further improvement with this approach. And in terms of the average hop count, it's a similar story. In average, it's about 15% further improvement that would have been possible. And to validate this, we also ran NOC simulations to actually get real latency numbers, which also account for congestion here. And then for MobileNet, we were 11.3% better, and for ResNet, 22.5% better. So that's quite promising results. So finally, we also took a look at the core load. And here the idea is that the slowest core dominates the throughput of our SoC. So we want to minimize this. So we took here a look at the difference in computational cycles of this, and what you can see, MobileNet performs much worse than ResNet. So what's the reason for that? And yeah, the reason for that is relatively simple. MobileNet has these depth-wise first convolutions, which have a really large memory footprint and a low computational footprint from pruning. So basically, this is just an intrinsic thing of the CNN, so we can't do anything about that, unfortunately. Okay, so to conclude our talk, What you have learned today is that snake mapping is a valid approach towards CNNs for edge AI accelerators, and that we could, with this, improve latency and power and enable mapping for the first time. But we also could show that further improvement of up to 22% in latency is possible if you use even naive optimization methods like simulated annealing. Thank you for your kind attention.